So today we are very happy to have Lorenz telling us about off-shell partition functions of 3D gravity.
Right. Thanks very much. And so I'm going to talk about the recent paper that I wrote. And so basically the topic is to understand the gravitational Hilbert space better and understand 3D gravity better in a canonical quantization framework. And we'll see that we can use it to compute various partition functions quite easily from this formalism. I also want to mention that many of the ideas that I'll talk about came about in discussions with Edward. And I should also mention that there is a previous paper by Alex Maloney who did something very similar. In some sense, this is a natural continuation of that paper. I'm sorry, I won't give very many references during the talk. Feel free to interrupt me to point out some references. So let's start. 3D gravity is a very rich theory, and in particular, it's much richer than in 2D. So on the one hand, there is no topological expansion. So meaning that in a two-dimensional theory of gravity, there's naturally some genus expansion, and we usually have some parameter associated to that, which is like the string coupling or S naught in the context of JT. In a 3D theory, there's no natural expansion like that. And so that makes the theory much harder to deal with. But in 3D, we still have no dynamical bulk degrees of freedoms. In some sense, the theory is still topological. We only have bulk boundary gravitons to deal with. So it's still much simpler than 4D. However, even though this is essentially a topological theory, it's still mostly unknown, I would say, how to compute various things in this theory. So there are, of course, some famous computations, but I would say it's fair to say that it's mostly unexplored, let's say, how to compute, say, partition functions and various other quantities. Even though, so some references I should give. Historically, Maloney and Witten, I think, were the first to try to compute the gravity partition function with a torus boundary and try to reproduce some 2D CFT partition function. And John B. Maloney and Witten, John B. Maloney and Dean computed many more one-loop determinants in 3D gravity. And then more recently, the problem was sort of reconsidered because these computations had various problems by the Princeton group. So it's Nathan Benjamin, Oguri, Chiral, and Wang, who pointed out that there are various negativities in this spectrum computed by Maloney and Witten, and they tried to cure it, and there are various ways one can try to cure it. So one idea is to include more contributions into the path integral by taking, for example, conical defects, which was explored by them, or then Joaquin and Henry Maxfield, they explored to include various off-shell contributions in the path integral. The principal one should include as well. So then Kotler and Jensen computed a 2-point correlator that is off-shell. So the geometry that will come back a couple of times in this talk that Kotler and Jensen computed. It's the partition function in this Euclidean wormhole that doesn't have a, so topologically, it's just a 2 torus times an interval, and it has 2 conformal boundaries, and there is no classical solution associated to that. And nonetheless, they computed some partition function. And so that made the ensemble interpretation of 3D gravity more plausible, perhaps. And finally, also in that direction, there was a recent paper by Scott, Hartman, Maloney, and Chandra, who also gave some ensemble interpretation of the boundary CFT. So I won't say anything more about ensemble versus non-ensemble interpretation. This talk will just be about trying to understand the bulk theory. And we won't say many things about the boundary theory. Okay, so that's just some references. Sorry for not writing them down. But so like in JT gravity, we learned that computing off-shell partition function is very important. Meaning by off-shell partition functions, I just mean partition functions on topologies that don't admit classical solutions. And basically what Saad, Schenker, Stanford told us is that in the JT gravity context, once you resum over all these all possible topologies, even including off-shell ones, then you will produce a nice boundary description in terms of the matrix model. So just as an example, in 3D gravity, let's say we want to compute the partition function with a fixed conformal boundary that is a torus. So then basically the starting point of this computation would be what Maloney and Witten did. And they said, okay, you should include all possible solutions with these given boundary conditions. So the first solution that you have is thermal ADS, but then you have various BTZ black holes that are basically modular images of thermal ADS. But then you could continue and try to include other geometries as well that don't admit classical solutions. So one that will come up in this talk is that, for example, we can take this Riemann surface that has one conformal boundary, one asymptotic boundary, but it's a genus 1 surface. And we can take this times S1. So this is a certain 3-dimensional manifold. And so it doesn't admit a hyperbolic metric, so it's an off-shell contribution, but you can include things like that and many others you can come up with. So in principle, the gravitational path integral says that you should sum over all of them and not just these on-shell ones. And so the question is how do you deal with those? And so all the manifolds that we'll look at today have some very simple form. And so essentially you can say we're in 2.5 dimensions or something like that, because we only look at 3D manifolds that have the form some Riemann surface times a circle. And so for example, this is true for this manifold, it's true for thermal ADS. It's also true for the manifold that Kotler and Jensen have computed, but it's more general than that. And we'll see that there's a nice way to compute these partition functions. And you can imagine that we use manifolds like this because they're easy to deal with in canonical quantization. Okay, that's more or less what we want to do and what was done before. With that, let's get into it and see what we can do about these partition functions. So to start with, I want to discuss the relation between 3D gravity and Chern-Simons theory. So most of the things I'm actually saying in the next half an hour or something are quite well known and you can find them in the literature. So most of the things won't be new. Only towards the end we have some new results. So on the level of the equation of motions, if you are in 3D gravity, then you can formulate it in the first order formalism, which means that you have a dry bind and you have a spin connection. In 3 dimensions, you can dualize the spin connection so that it has only one index. And then the standard statement is that you can form these combinations, let's say A plus minus, that are EA mu. That's 1 over L omega A mu, where L is the ADS length related to the cosmological constant. And if you form these linear combinations, then you get formally some SL2R gauge fields, and you can check that the equations of motion of gravity just translates to the flatness of these two connections. And the flatness condition is just the equation of motion of Chern-Simons theory. So on the level of the equation of motions, 3D gravity really does have equivalent equation of motions as Chern-Simons theory. But I want to emphasize a little bit more that they're not the same. They're the same on the level of the equation of motion, but there are at least 2 main differences that will play an important role. So the first main difference is that in gravity, we're supposed to gauge by all diffeomorphisms. So diffeomorphism by gauge freedoms. And also in Chern-Simons theory, there's a gauge freedom that is coming from SL2R times SL2R. However, the gauge freedom in 3D gravity is slightly bigger than in gauge theory because there are large gauge transformations. And these large gauge transformations are usually called mapping class group. So the mapping class group are just all diffeomorphisms of your 3 manifold modded out by all diffeomorphisms that are small, that are continuously connected to the identity. So this is some group, and probably for the Riemann surface case, you're quite familiar with them. Let's say, for example, our manifold. Let me just convince you that you all know the mapping class group. So, for example, the mapping class group of a 2 torus is just SL2Z, because you can just decide to map. I mean, these are literally modular transformations. These are the large diffeomorphisms on the torus. And there are generalizations of this to higher genus surfaces. And in gravity, we're supposed to gauge also the large diffeomorphism, whereas in a theory of, if you're just knowing about gauge theory, you have, say, gauge theory and a 2 torus, then you usually wouldn't gauge SL2Z. So that's one difference. And the other difference that I want to highlight is that in gravity, the drybine is invertible by definition, because it's square. If we form the definition is this. Sorry, AB is G mean. So this drybine makes up the metric, and the metric should be non-degenerate, and so similarly the drybine should be invertible. And again, in the gauge theory description, there's no reason why this should be the case. Okay, so these are the two differences. I'm sure you can find more, but these will be the relevant ones for this talk.
So what you just said means that in Chern-Simons, we can find classical solutions that don't come from solutions of gravity.
That's right, yes. So for example, one trivial thing you could do is to take A to 0, the trivial connection that has a flat curvature, but then also E would be 0, and that's not a good drybine to have in gravity.
So the case is, I mean, naively one might think it's a measure 0 set of solutions.
But it's not, because you have to be invertible at every point in space-time. Right. That's what's making not measure 0. But you'll see in a second what that implies in the canonical quantization context. And there it's quite important. Okay, so if you know about this relation of gravity to SL to Chern-Simons, and one thing, maybe I should add a third thing, is I haven't talked about the global structure of the gauge group. So there's, we just formed these combinations on the level of the Lie algebra. So there is some discussion also what is the global structure of the gauge group. And I think the most natural one to assume this, that is actually PSL2R squared, or SL1,2. Because that's the natural structure group that you have in gravity, not SL2R like people would usually say. Okay, so the most natural, so the naive guess for the, say, we want to find the gravitational phase space on some Riemann surface sigma. Then the relation to PSL2R would maybe suspect perhaps that it's just given by 2 copies of the modular space of flat PSL2R bundles. I mean, this is just a fancy way of saying all the connections A that satisfy F, they're flat. Okay, and this is wrong because of precisely these 2 issues. So the first issue is that there's a mapping class group that acts on these PSL2R connections, and the correct way of acting on them is by a diagonal action of the mapping class group. So in general, there's a mapping class group action on this component and on this component, but we want to act on the diagonal. So this should be kind of familiar from, say, CFT, where you want to impose that, say, your torus partition function is invariant under SL2Z, but you're imposing it for the full torus partition function, not for the left movers and right movers separately. So this is the kind of analogous statement in the gravity theory. And the other issue with this is that the modular space of PSL2R connections actually is a disconnected space. So this has several components. And for example, the component that we said before, so okay, let me just mention 2 components. So we have the trivial connection in there. So that was the trivial solution that we found before that we didn't want to associate with any gravity solution. And so that's sort of a bad PSL2R connection that we want to throw out. But we also have what's known as a Teichmüller component. Let me just call it T. So the Teichmüller component are PSL2R connections that come from a hyperbolic structure on the Riemann surface. So whenever you have a hyperbolic structure on the Riemann surface, then its tangent space is a flat PSL2R bundle. And not every flat PSL2R bundle can qualify as a tangent space. For example, the trivial one cannot. And that is actually disconnected from this one. So they're not continuously connected. It's not just an open subset. In general, this modular space of connection, let's suppose for the moment that we are on a compact Riemann surface, but there's a similar story for an open Riemann surface. So there are components. Okay, yeah, I mean, just look at this. So in general, there's a topological number that labels these components, which is the Euler class of the bundle, and can run between 2 minus 2g and 2g minus 2. And the trivial connection has 0 Euler class. So that will be for the trivial connection, whereas the Teichmüller component has top Euler class. So that's the Euler characteristic of a Riemann surface. You can take this or this, they're complex conjugate. It doesn't matter. And so then what mathematicians proved, so this was proved by Krasnov and Schwenker, is that the invertibility of the Dreibein is actually equivalent to taking just the Teichmüller component. So if you pick an element in the Teichmüller component of these flat PSL2R connections, then this actually gives you a 3D metric where the Dreibein is everywhere invertible, and vice versa. All right, so that gives us the correct modular space now. The correct modular space is that you take 2 copies of the Teichmüller component. Let me denote one by T and the other by T bar, because one should be, you should take the complex conjugate of the other one. And then you divide by this diagonal mapping class group. Okay. So this is one description of the phase space of 3D gravity. And so in terms of canonical quantization, there is an immediate problem to this. Because let's suppose that we are on a genus 2, compact genus 2 surface. So that's maybe a little bit boring because we want to eventually add asymptotic boundaries. But let's just try to, let's say sigma is some genus 2 surface. And we want to compute the gravitational partition function that comes from sigma times S1. And since this is a topological theory, we should just compute the dimension of the Hilbert space on sigma. So we should quantize this phase space and compute the resulting dimension of the Hilbert space. The problem is that this phase space is actually non-compact because Teichmüller space is a non-compact space, and you don't cure that by just dividing by this diagonal mapping class group. And roughly speaking, every unit volume of phase space will give you one quantum state. So if you have a non-compact phase space, you will get infinitely many quantum states. And so what that results is that the partition function on this genus 2 surface times S1 is simply infinite, because there are infinitely many states. So that I find a little bit boring, and I don't really know what to do with this. And so it seems like most of these, so essentially all of these partition functions will be infinite. There's just some very few number of cases where you can actually get finite results.
One question?
Yeah.
Did people try to define some compactification of that, like?
Yeah.
In case of...
Yeah, so you can compactify the Teichmüller space in various ways, but then it has literally a bound. I mean, you get a space with a boundary. You don't get a compact space. So then you still have an infinite number of states. It doesn't help you for that.
And presumably the volume of phase space is something. If it is infinite, you want to cure it by something.
Yeah, exactly. Yeah. Okay. So you can just add some asymptotic boundary, but it doesn't happen.
Can I ask a question?
Yeah.
Do you know if the non-Teichmüller components have any interesting physical interpretation, like maybe in terms of non-smooth hyperbolic geometries or anything like that?
Well, you could think that because I mean they would have interpretations in terms of geometries with singular metrics,
right?
With metrics that are not invertible everywhere.
Yeah. Do you know what they look like? I mean, is there anything to say about them that's interesting?
don't look like any manifold because they don't have a good metric on them, but
Didn't you tell me a version where they have only isolated singularities?
Oh, you mean that? Yes. So you can, for example, I think what you're saying is that one way of thinking of them is to take an ordinary manifold, like ordinary Riemann surface, and then you put conical excesses at some points. And if you put a conical excess, let's say of axis angle 2 pi, then this changes this Euler number by 1 unit. And so that's one way to think how you can access these other components. So if you want, you can think of these as being, for example, manifolds with conical excesses. But if you take conical defects, that won't help you to lower the Euler number. You really have to take x's.
Great, thank you.
But I mean, it doesn't get like they're still all non-compact and they become even worse. So for example, the trivial one has quite bad singularities, whereas the Teichmüller one we know is a contractible space. So the topology becomes much more complicated if you go to the other component. So I might end here my talk, but let me not do that and go on. And let me just propose a simple solution for now, that we just consider different theory. So let's just consider chiral gravity. So chiral gravity is just a theory that is still related to Chern-Simons theory, but on the Chern-Simons side, in principle, there are 2 levels for the left movers and the right movers, and you can choose them independently. And so the most extreme thing that you can do is to choose one of the levels to be just 0. So chiral gravity is a simpler theory of gravity, provided it's consistent anyway, and it's just related to one copy of PSA2R Chern-Simons theory. So, and holographically, you would expect, if this theory makes sense, that it's dual to a theory that has just left movers. So it's like a holomorphic CFT. So that you would expect to be simpler. And the nice thing, if you do that, is that its gravitational phase space is one copy of Teichmüller space only, divided by the mapping class group. Because the level being 0 on the, say, the right movers just means that they completely decouple. And so Teichmüller space mod mapping class group is nothing else than the modular space of Riemann surfaces. Okay, I have too many m's. Let me call this. Okay, let me suppose it's some compact surface, and then this would be mg, the standard notation for the modular space of Riemann surfaces, where g is the genus. All right. I think I'm allowed to continue here. Okay, and this one is much nicer because actually, as you all probably know, this one actually does admit a natural compactification in the sense that we really get a compact manifold without any boundaries. So let's compactify. If we compactify, we get this compact phase space that is just the Deligne mum for compactification of modular space. Okay, and so now we have a much better chance of computing all these partition functions because we do have a finite compact phase space. And so then one more ingredient that I should tell you is what I just told you what the phase space is, but there's also symplectic form that you have to know on this phase space because it's a symplectic manifold. And there are various ways to derive it. For example, from the Chern-Simons perspective, you can easily see that the correct symplectic form is the Weil-Petersen form. Actually, it's k times the Weil-Petersen form. It's some normalization of the Weil-Petersen form. I'm not worrying about factors of 2 pi. Okay, so our task now is very clear. So we have this phase space that is just a modular space of Riemann surfaces with the Weil-Petersen form, and we should quantize it. So we should associate some natural Hilbert space to this phase space. So that's, unless there are further questions. Right, do we have any questions? Okay, and
exactly is this Deligne mum for compactification?
what it is or how it's defined? Or?
Yeah, how it's defined. Say it quickly if not.
Right, good. Yeah, I should have said that, correct? So it just it's the natural compactification that you would know, for example, from hyperbolic surfaces. I think that's the easiest way to say it. So, for example, if you have some hyperbolic genus 2 surface, then you know that you can pinch, say, this cycle in the middle. And if you do this topologically, you get some surface that looks like two touching genus one surfaces, but they have this nodal singularity in the middle. And the minimum for the compactification is simply the compactification of modular space that you get if you allow nodal singularities. So you allow nodal singularities, but for example, this one would not be allowed because it's not allowed in the hyperbolic case. So the middle component would be a sphere with two punctures, but you know that this doesn't admit a hyperbolic metric if you just have a sphere with two cusps. So this one would not be part of the compactification, whereas this one would be.
I think it's worth remarking that if we allow such nodal surfaces, then in JT gravity, we would not say that we are using off-shell configurations.
Yes, yeah. That's right. Sorry. Oh, I thought that's not correct because you need to. So the equation of motion of the dilaton are certainly satisfied because the curvature is negative. But the question is whether the equation of motion, I thought the equation of motion of the metric tell you that there needs to be a killing vector on the surface. The killing vector.
And the dilaton, it's proportional to the dilaton. So the dilaton is just constant on the compact components.
Yeah, you have a solution which is, let's say, Poincare coordinates. There is some dilaton, right? And then you just compact away that.
Yeah. Okay, so with boundaries, then you would have something like this. Say there's some massive. So then there's the dilaton. So there's a killing vector that rotates that, and it's just constant. So, yeah, I agree. Okay. Okay, but yeah, for us it will be quite important that we this compactification.
And that constant might be minus infinity.
Here.
Yeah.
Yeah, I don't know.
Maybe not.
I mean,
No, I think I'm wrong. Sorry. No, it's 5 0. It's just the 0.
yeah, the on-shell action I think should be 0. Okay, so let's not be too much scared of this word quantization of this modular space. And so let me briefly tell you what the recipe is to quantize the space, and then let's do an example. That's really something quite easier. So let's use something that's called Keller quantization. So the modular space of Riemann surfaces is not just some arbitrary symplectic manifold, but it's actually more than that. It's a Keller manifold, or more precisely Keller obifold. And whenever you're in this situation, then there's a natural way to quantize symplectic manifold. Whereas just a vanilla symplectic manifold, it's hard to quantize usually, and you need to make some choices. So we're in this lucky situation that we have actually Keller structure. And then geometric quantization tells you the following. So if you have a Keller structure, then you can pick a line bundle. Let me call this line bundle L to the K. So this line bundle will depend on K. And so there's a line bundle L that doesn't depend on K. And for K, I just raise it to the Kth power. And this line bundle is determined by the property that its curvature, meaning that, its first Chern class, which is the cohomology class of the curvature, is simply the symplectic form that we want. So you can pick a line bundle whose curvature is simply the Weil-Petersen symplectic form. So this is often called pre-quantum line bundle. And then we're almost done already, because then the states in the Hilbert space that we want, let me call it H, are just identified. So this Hilbert space is nothing else than holomorphic sections of L to the K. So in this, we're in a simple situation where we just want to know about the dimension of the Hilbert space. We're not caring about some natural operators at the moment. We could do that as well. So we're not caring about some operators that act on the Hilbert space. We literally only want to compute the dimension of the Hilbert space for a compact surface. And the Hilbert space you can identify with holomorphic sections. The reason that they're holomorphic is roughly because they're in a quantization, you should have momenta and positions. And the fact that these sections only depend on holomorphically on the coordinates is kind of the analog of saying is that they only depend on positions. So this is like the analog of L2 of R or something that we do in quantum mechanics. So that you only have functions that depend on the positions, but not the moment, or vice versa, whatever you. So this is more like a coherent state quantization. So I just want to. So our task is very clear, and let me just. So the mathematical notation for this will be that we're taking all sections of this line bundle, which is just the zeroth cohomology. And so now this kind of abstract recipe is.
Does this line bundle have some holomorphicity requirements?
Some holomorphicity
requirements.
Yeah, it's a holomorphic line bundle. Yeah, sorry. Otherwise, it wouldn't make sense to say that we have holomorphic sections. So this line bundle is actually uniquely determined by this property, up to isomorphs. And so now, once you study this problem, then actually it gives a very simple answer to what is the 3D gravity partition function on some Riemann surface time circle. So for the moment, still sigma will be compact. We'll relax this later. So it's simply the dimension of this Hilbert space. So all we have to compute is the number of sections of this line bundle. Once we count this number of sections, then we know what the gravity partition function is. Okay, so that's maybe slightly abstract. So let's make a simple example. The example I want to make is M11. So strictly speaking, this is not has a puncture, but this is a case that is very familiar to everyone. So let's try to quantize M11, which is just the upper half plane modded out by SFT. And so there is a relevant line bundle, and L to the K turns just out to be, if you look what the Partition form is, L to the K is just this the line bundle of modular forms. So meaning that sections of these holomorphic sections of these line bundles are modular forms of wave K. And
so what is M11 is the torus with one.
Yeah, the one puncture you just need because the torus has like a U1 times U1 isometry group. So to make it stable in mathematical language, you need to fix one puncture. And so, I mean, but you don't have to worry about this. This is literally just the upper half plane mod SAT. That's the standard.
Normally, we say that the moduli space of a torus is the upper half plane mod.
Well, yeah, mathematicians would say it's M11. But so the thing is that you should mod out by all automorphisms. Like in the string or something, we would divide by the volume of the automorphism group. Right. So mathematicians would divide by all automorphisms, and so they would divide, say, this by U1 times U1 or something like that. And so this would not be compact, would not be a nice moduli space because it has this continuous quotient. So mathematicians usually don't consider the moduli space of just the torus. And that's consistent with our intuition from the torus from the hyperbolic. So because I told you that this space is you can define in terms of hyperbolic surfaces, but a simple torus without puncture doesn't admit a hyperbolic metric. So if you look at torus with one puncture, then its moduli space is in fact this. So yeah, this is just a fancy way of saying this. And then the natural line, so there's essentially only one line bundle on M11, and it's this line bundle whose sections are modular. Okay, is that clear to everyone? I feel like it's because it's not clear to Juan. How do I fix K? K is the level of PSL2R. Maybe I haven't said that in this. So if you track what K is actually the L over I think 16 G Newton. So it's related, and in particular 24K will be the center charge of the dual safety. That's the simple way to remember it. So yeah, K is related to basically the curvature ideas. Other questions? So now, hopefully, many of you have seen modular forms, and the ring of modular forms is just generated by E4 and E6, the fourth and the sixth Eisenstein series. And so, what now the Hilbert space is, so that you get by quantizing M11. Well, Igor, I should also say that K plays the role of 1 over H bar in this quantization. So this Hilbert space that depends on K is just, so we have this ring of modular forms that is is just generated by E4 and E6, and then you choose the component, like the degree K component. That's some Hilbert space. And so knowing that it's generated by E4 and E6, we can simply compute its dimension. Okay, so in this case, the dimension of our Hilbert space is just the Taylor coefficient x to the k of 1 over 1 minus x to the fourth, 1 minus x to the sixth, because that's the generating series of the ring. And if I write it out, I get, I think, k. So first of all, I get 0 if k is odd. I just want to write it once. I get k over 12 if k is 2 mod 12. And I get k over 12 a floor, so meaning rounding down, plus 1 if k is 0, 4, 6, 8, or 10 or 12.
Is it the case that the Chern-Simons coupling was only properly quantized if k is even?
No, that's not the case.
Well, it's very strange then to get 0, though.
Yeah, it's so the reason why you get 0 is a special thing about the torus. And the reason is because every torus has a Z2 automorphism. And the Z2 automorphism prohibits any sections of odd weight. So if you compute, for example, the genus 2 partition function, then it would be non-zero even if the k is odd. So the quantization in Chern-Simons, I should also have mentioned this probably, is that k is an integer.
So what's the connection between the Z2 automorphism and the conic systems?
It's just that if you have a modular form, so modular forms are defined to have this transformation property. And so let's consider tau going to right. This is working. So if you consider -1 over tau, then you set C. Okay, the problem here is that this transformation is defined over PSL to Z, whereas here you have to commit to a sign of C and D. And if k is odd. So that's, I think, a simple way of saying. So, but you can see that this doesn't have any solutions because their sign is inconsistent.
So I wonder, is this an anomaly or a Gauss law that makes it vanish for k odd?
No, it's not an anomaly. It's.
Are you sure? What's this extra thing too?
I'm sure, yes.
It's not a diffeomorphism anomaly.
Well, I mean, the more kind of intrinsic way of saying what these sections are that there's, so every torus you can specify by defining a sublattice of the complex plane. And now, so these sections are some functions of lattices, so lambda is some sublattice, and they satisfy some homogeneity property.
Yes, I know. Yeah.
But so you can define that completely without appealing to some basis of ABCD.
No, sure.
There's no anomaly, and these line bundles are well defined. They just don't have any section. And yeah, you can see that in various ways. But the fundamental origin is that there's a Z2. A generic torus has a Z2 automorphism.
I'm thinking that the Z2 can be thought of as a gauge symmetry, and the oddness under that Z2 is interpreted as an anomaly, and that's why this must vanish. It's either that or
I think that there's an anomaly, but it's true that you can interpret this as a gauge symmetry because it's part of the residual mapping class group or whatever you want to say. So and it just throws, so it acts odd on all
So it's either an anomaly or it's a Gauss law. Maybe it's a Gauss law.
I guess we can call it Gauss law. Yeah, I guess we can call it Gauss law. But this is really exceptional to the torus. It will not happen for any other surface. I can promise you. Okay, so but the main reason I wanted to write down this formula is just that I want you to notice that it's sort of complicated. It's not a nice formula. It doesn't depend on K in a very simple way. So usually, that is maybe a discouraging sign because K, remember, was related to the Newton constant, or it might be an interesting sign. So it's already an indication that this partition function will depend in very strange ways on the Newton constant in the theory. Okay, so that was my example. So let's discuss a little bit, and now let's go again to the case without any functors. So if we would have manifolds, then you can actually compute what is H0 of, say, M is some manifold now, not an orbifold, but some compact manifold. And there is, again, some line bundle, like we have just said now. Then there is an index term that computes this number of sections. And the index term says that you should integrate over M, should integrate some characteristic classes. And you don't have to precisely know what these characteristic classes are, but essentially there is some characteristic class depending on only on the manifold, on the tangent bundle, and that's the top class. And then here in the exponent, sorry, I should have written C1. The first, you get the first Chern class of the line bundle. And you just, so these, you can just think of this as being some differential form. And
higher cohomologies vanish.
That's what I was about to write. So for this to be true is that you need to assume that higher cohomologies, let's say HL and LK, are 0 for L bigger than 0. So that seems like a very strong constraint, but you can actually show, so this is usually true in various circumstances because of Kodera vanishing. So there are some theorems that ensure you this. In particular, in our context, this is true if K is at least 3. So I'm not sure what happens if K is 1 or 2, but if K is at least 3, then this higher cohomologies will be vanishing on the modular space of Riemann surfaces, and you can use some theorem like this. However, there's another caveat. So this is one caveat, and so you might be very happy about this, but for orbifolds, this is actually also not true. And you can already see that this won't be true because the right-hand side here will always be a polynomial in K. So this is some differential form. You can expand this in K. We'll give some power series in K, and you stop at the dimension, at the top dimension of N. So this will be some power series in some polynomial in K of degree being the complex dimension of modular space. And so, for example, if we would try to apply this for M11, we get some polynomial that has a constant term and a linear term. Let me just write you down what you would get if you just blindly put in what the right-hand side is. So it's K plus 5 over 24. We get some result like this, which indeed is some function. And however, I want you to notice that this is not a completely random function. It has something to do with this result. So first of all, let's ignore the plus 5. So we roughly get K over 24. And you see that this is roughly also what we get here, because half of the time we get K over 12 and half of the time we get 0. So what happens, and you can show that this always happens, is that this in some sense gives an average in K. This has nothing to do with the usual average discussions in physics that we have in the last couple of years. So this in an average sense gives the correct result of sections. And mathematically what's happening is that for orbifolds, there is a corrected index term. It's called the Kawasaki index term that has additional terms in this integral. And they roughly speaking correspond to twisted sectors. So what we computed here is the untwisted contribution to the number of sections. And then you should add some twisted sectors to it. And once you add all the twisted sectors, you can check that you actually get this. And
the issue is that the moduli space is an orbifold.
That's right,
so
yes.
The Riemann surface is an ordinary manifold, but the moduli space is an orbifold.
That's correct, yeah. And so in particular, maybe just to get back to the 0 versus non-zero, So the fact that there's always a Z2 automorphism means that there's another term that you should add to this. There are yet other terms that come from the more exceptional automorphism groups of tori, but there's always another term like this that comes from the Z2 automorphism that would give you the same, but with a -1 to the k. And that is how you see this 0 versus 1. But these other terms typically come with phases, so like -1 to the k. And so, so that it's always true that this gives some averaged sense of this number of such. And the +5 you can also understand because there are 5 times a +1 here. There are 5 cases here. You get a plus. So you see this is not completely random. And so in general, it will be true that this is very complicated to compute, but this is quite simple. And so let me define something that I call fake partition function, because this is what mathematicians call fake Euler characteristic sometimes. So let me call this fake partition function on some Riemann surface times S1. And you can just take the naive integral over the modular space of Riemann surfaces. And then you do this dot class e to the k. Okay. So I think that's all I wanted to say about, and you can show that this behavior generalizes and it becomes more and more complex. So if you compute the actual partition function, say on some genus 20 surface or whatever, I don't know how to compute it, but you can see from this index theorem that we'll have all these phases in it, and it will become more and more complicated function of k with all these random phases. And maybe that gets some of you excited, but I don't know what it means. So there are some phases in these partition functions that depend on the Newton constant in some non-trivial way. And so what's often said is that this gravitational path integral cannot reproduce these kind of erratic partition functions. That is not really true, because there are some examples here that that have very complicated, like non-polynomial behavior on the Newton constant, which I think is also not something that you would have if you have some semi-classical evaluation of the path integral. At least I don't know how to get this. Okay. Do we have any more questions on the compact case?
Small question, how useful is that theorem to deal with orbifolds? Like if you pick some value of, I don't know, some specific, I don't know, some case that, can you really like use that formula to compute it?
I don't know, I hope so. I haven't really, I've just computed for M11 and checked that it comes out correct. But, and some, you see some general properties. So in general, there's one term for every, say, sub-manifold in modular space of Riemann surfaces with given automorphism group. So for example, on M11, there's a term, so for every Z2 automorphism, because there's a Z2 automorphism, that gives a term. And then because there are some tori with a Z4 or Z6 automorphism, that gives more term in this series. And so on some higher genus modular space, you need to know all the possible automorphism groups of the surfaces and what their submanifolds are. And in general, this, like the integrals that you get for the twisted sectors are integrals over these sub-modular spaces of fixed automorphism. So I don't think it's very practical for ideas, but maybe.
Lorenz, I don't know what you were referring to just now, but I mean, you know that you can use a semi-classical evaluation to get things like Rademacher series, which reproduce coefficients of modular forms, for which there's no simple analytical formula. There's, you know, they jump.
So you mean semi-classical evaluation of the gravitational path integral, or of what?
Well, it's a more complicated theory, like a string theory or something like that. But you know, Samir, for example, has very carefully done a semi-classical approximation and gotten.
Right. The problem is that I don't know of any semi-classical approximation to these partition functions because they don't admit.
Something about the ones that you made some general remarks just a moment ago that I'm not sure I agree with. That you can't get you know, number theory.
Yeah, it might be possible, but I mean, also mathematicians don't know what happens at genus 4 and beyond for sure. So I mean, it's for sure true that it gets very hard. So there might be some approximate way of computing it, but approximate way of computing is basically what I will show you how to do now.
Now, I'm just pointing out that arithmetically interesting functions can be obtained from a semi-classical expansion.
Okay.
And the you know, the semi-classical derivations of things like the Rademacher expansion of coefficients of.
Okay, if you mean by semi-classical large K, because K is like 1 over h bar, then indeed you can do things like that. and the leading term will just capture the volume of moduli space. Because in large K, you can forget about this, and things like that you can do.
No, the Rademacher expansion is exact. Anyway, we can argue about it later.
Okay, I don't know exactly what expansion you mean, but all right. So let me now come to the maybe most interesting part. So until now, everything was pretty formal, and maybe unfortunately it also remains a little bit formal. But we will now study things that are of much more physical interest. So, for example, our motivating example was to compute the partition function with a torus boundary. So, in particular, for example, you might want to try to compute this partition function, which again doesn't admit a hyperbolic metric. Okay, so we have to generalize now the setting that we computed, that we considered to the case with asymptotic boundaries. And in this case, we want to compute a partition function that is not just a number, but it depends on the beta parameters or the modular parameters of the boundary tori. So we want to compute something like this, where Hi are the boundary Hamiltonians. And mathematically, you can do this quite elegantly. And essentially what this means is that, so there's on these moduli spaces, there are various U1 actions because the boundary Hamiltonians, they describe time translation in the boundary theory. And correspondingly there, since all the degrees of freedoms are, say, left moving, it doesn't matter whether you take time translation or spatial translations in the boundary theory. So if we have some Riemann surface like this one, then the time translation in the boundary acts by along this S1. And since all degrees of freedom are left moving, they're coupled to the rotation along the spatial boundary circle. And so the Hamiltonian that describes time translation also describes rotations of the boundary circle. And so what that means is that if you now look at the relevant moduli spaces, then they admit U1 actions they admit a U1 action for every boundary. So one way to think about this that is analogous to how we deal with it in JT gravity. So let's say I just redrew that surface in a different way. There's an asymptotic boundary here. Then you can define the asymptotic boundary by doing some sort of weakly cutoff near the boundary. And the shape of this weakly cutoff is dynamical and describes the boundary graviton degrees of freedom. So the relevant moduli spaces will be infinite dimensional. So in the simplest case where you just have a disk, this moduli space is kind of well known, and this diff S1 mod PSK2R. The diff S1 describes the shape of the cutoff, and then we have to divide out by the automorphisms of the disk. So let me denote the moduli space. I don't think there's a standard notation, but let me denote it by the moduli space of genus G with n asymptotic boundaries. And again, we'll compactify this, which we can define again using hyperbolic surfaces, let's say. So it's just what we do in JT gravity. Usually we don't phrase it this way. Usually we drew the trumpet to the bulk part and so on. But I would just want to do everything in one go. And there is a phase space that describes both the bulk degrees of freedom and the boundary gravitons. And in the simplest case, as I said, this M0, 1 is just PSK4. Sorry, diff S1 not PSK4. Okay, so we want to still quantize this phase space, but taking care of the U1 actions now. And so essentially what that means mathematically is if there's U1 action, it means that we want to do everything equivariantly. Okay, so in particular, so let's say we want to compute the simplest partition function. So this my notation is that I'm writing ZG. Oh, I wrote it, yes, ZG and of n boundary parameters. So this is just the disk partition function or disk times a circle. So it's the same thing as term radius. So if we compute that partition function, that will be the same as the vacuum-Virasoro character. And so we can use the same strategy. The strategy was, or one strategy is to compute these integrals. And so we can compute an integral over diff S1 mod PSR2R of the top class times e to the AC1. So there is still a Peterson form on this infinite dimensional space. And this seems like a very complicated thing to do because it's some infinite dimensional integral. And all these things depend on beta now because they are the equivariant first Chern class and the equivariant top class. And that correspondingly takes care of the U1 action. And so that seems very complicated. But one very nice thing is that if you have these equivariant integrals, then there's a theorem in math that tells you that equivariant integrals localize, provided that the integrand is equivariantly closed. And so equivariant localization tells you that this reduces to an integral over the fixed point set. So there's a U1 action on the space, and there will be some fixed points or some fixed manifolds under this U1 action. And equivariant localization tells you always that you can reduce these integrals down to ordinary integrals, non-equivariant integrals over the fixed point set. And it's maybe I'm saying it in the fancy way, but it's something that physicists know very well because, for example, if we do supersymmetric localization, we're doing precisely that. We're choosing some U1, and then we're doing equivariant localization with respect to this U1, and we're localizing on the fixed point set. And once we do that, there's some one-loop determinant. Mathematically, this is known as the Euler class, the normal bundle of this submanifold in the big manifold. But you know, like that just keeps track of the normal fluctuations of that submanifold in the big manifold. So that's some mathematical theorem that we can use, but we use it all the time, probably just not in that language. And so in the case of the disk, it's very simple to see what is the fixed point set. So the U1 action rotates the whole picture around. So what's the fixed, the only fixed surface is where this cutoff is actually a round cutoff, because then it's invariant under rotation. And that's a single possible surface. So there's a single fixed point in this case. And you can compute these Euler classes and so on. And what you find indeed is that you get e to the k beta, that comes from this first Chern class. And then you get an infinite product, which comes from this Euler class. And this infinite product precisely reproduces the Virasoro vacuum character. And it's a vacuum character for the correct central charge. So you might say this is some horribly complicated way of computing something that we know. But the nice thing about this is that this completely will generalize to different, more complicated situations. So I should stop soon. We'll do that. So in general, what equivariant localization does is if we want to compute, say, some more complicated situation like this one, with this wiggly cutoff, and might be some holes in here, then this will, again, there's a U1 action that rotates the whole picture around. And you might think that there's never a fixed point like that because it rotates the handle around. So it seems highly unlikely that there's a fixed point. However, there is actually a fixed point once you remember that you should work in the compactification. So the fixed point looks like this. So because now you have this, you can think of this either as a nodal singularity, or you can think of it as being like an infinitely long throat. So if you rotate here, then this will actually not rotate this part of this. And again, I shouldn't have drawn this in a wiggly way, but I should have drawn it in a round way. So it should be invariant under the U1 rotations. Okay.
In this compactification, we can rotate the right side to the left side.
Yeah, that's right.
That you pick, you have an equivariant.
Or is
it obvious that any section that you pick, you have an equivariant extension?
Well, I didn't talk about sections so far. I just talked about the index term. And you might be worried because this is technically computing this fake partition function. For that, this is correct. There's always an equivariant extension. So you can show, for example, there's an equivariant extension always of the tangent bundle and of divided Peterson symplectic form. There's also an equivariant extension. But we haven't talked about sections. Right, and in this case, this is actually exact because DFS1 multi-sector doesn't have orbifolds. In general, so this fake versus non-fake business only shows up at higher genus, because genus 0 surface with arbitrary number of asymptotic boundaries will never have orbifold singularity. So there, the fake partition function is computing the actual partition function. But okay, so if you use this equivariant localization, let me just write you down the result. It boils down everything again to computations on the ordinary modular space of Riemann surfaces. If you want to compute the genus G partition function with some number of boundaries, then you get the product of Virasoro characters, now not vacuum characters, like this. And then you get sum over integers L1, L2, so on bigger than 0. So this is just the ordinary Q expansion. And then the second line is the partition function of primary states. This just takes care of the characters. And this is the Q expansion of the partition function. And then we again have to compute a certain homology class of some line bundle. Now it's on MGN because the fixed point set is isomorphic to MGN. In this case, it will be M11 because there's one fixed point. And then the line bundle is slightly modified. So it's LK, but then tensor together with other line bundles. We call them double L. And okay, so these line bundles, I don't want to get into too much details, but there are some natural line bundles on MGN that you can construct. And for those who know,
the Mumford and Morita classes, those line bundles.
Sorry, what was that?
Are they related to the Mumford classes?
Not to the Mumford class, but to the psi classes. So there are n of them, and the first term class are the psi classes. So there are the line bundles. So the psi classes are the usual classes that people consider in, say, topological gravity, and Edward has his famous conjecture on their intersection. So these are quite well under control. Right. So, and okay, so I should stop. So one thing I want to mention before I stop is that, so this again is some algebraic geometry problem, and you can use it, for example, to compute Z1 with one asymptotic boundary exactly, because again, everything boils down to things on M11 that we studied before. And this whole thing will boil down to counting, again, modular forms. So you can give exact formula of Z1 beta. That's this topology. And the formula is again quite complicated. It involves these phases and so on, or case distinction. So it's not a simple formula. So that's the main thing I want you to take away from it. And I don't want to write it down because it will take me too long. But in general, I don't know how to compute these numbers of sections exactly. So one thing that I do know is that how to compute this fake partition function in general, which is this averaged notion of partition function. And so that is relatively easy to compute because it boils down to computing integrals over MGN. Because this model, this index theorem boils everything down to computing integrals over MGN. And there is a machinery in math that computes these integrals. That is topological recursion. So you can, so topological recursion basically tells you that whenever you have some integrals of characteristic classes of MGN, then there's a recursion relation that you can define that computes these integrals. And it's a recursion in the genus and the number of pointers. So there is, and for JT gravity, we're very familiar with this again, because it's just the loop equations of the dual matrix model that recursively define the partition. So there is a topological recursion that computes fate. Just for those who know, there's a spectral curve you can compute. So the spectral curve, or this first differential that goes into the topological recursion, is sine bz sine b inverse z dz, where b is the usual parameter of Liouville theory. So if you write c, that was 24k, that's 1 plus 6 b inverse. So that's related to k. Then this is the that's the spectral curve of the model. You can compare that so with JT gravity. In JT gravity, the spectral curve is sine z times dz. So usually people don't write this part, but that is the spectral curve in some normalization. But and you see that if you send b to 0, then this becomes this, because z is an auxiliary parameter. You can just rescale. That's perhaps what you expect, because you can show more generally that this model actually, if you send k to infinity, it reduces, and at the same time you send beta to 0, it reduces to JT gravity. Although with a kind of strongly coupled JT gravity, because the genus counting parameter is large and not small. All right, I think, well, let me, if I'm allowed, make one more remark on the non-chiral gravity, because now we spent all this time on the chiral gravity case. And in the non-chiral gravity, you can repeat essentially all the same exercises, except that in most of the cases you get infinity at the end. In particular, you can again write down what is the fake partition function on a genus G surface. And actually, in all the cases where it's not divergent, the genus is 0. And it depends on some boundary modular parameters and some formula that you get this. Now you, instead of summing these L's that you can think of as being the left moving conformal weight, you should integrate over the left and right moving conformal weight, with the only restriction being that their difference has to be integer. Then there's some measure factor that's slightly subtle to fix that I think is 1 over root imaginary part of tau. And then we should have qi to the hi, q by I bar to the hi bar, where qi is e to the 2 pi tau. And then again, you have to compute some dimension of some sections. But now these sections are not holomorphic sections. So let me call them gamma. So there are sections on MGN of a line, still a line bundle, but not a holomorphic line bundle. It's a complex line bundle, but not holomorphic. This line bundle is L absolute value to k, by which I mean that kind of the overlap maps that define this line bundle are just the overlap maps of LK times the complex conjugate, and then times the natural thing that we would write down, L1 bar, H1 bar, and so on. And so this, but here these are just literally sections. They're not homomorphic sections or something. So as soon as the manifold, as this modular space has positive dimension, then you're screwed, because there are infinitely many functions, and similarly there are infinitely many non-homomorphic sections. And in this case, this will just give infinite. So this formula essentially only works if genus is 0 and n is 3. And you can also deal with the nx g to 0 and nx2 case separately. And that is exactly the case that actually Kotter and Jensen computed. So if you want, you can compute one more case that is the 3-boundary wormhole, but after that, you have to stop and you get infinity.
Is there any magical self-adjoint operator that acts on this space of sections that you could then grade that infinite dimensional gamma space?
Not that I know.
Laplacian. There's a Laplacian.
Oh yeah, so
Laplacian or something. Then you could grade that by the eigenvalues of the
yeah, you can do that. Then you could compute some heat kernel instead of the dimension. Yeah, but I don't know what it would mean physically. But yeah.
Can I ask maybe a naive question? So now that we have 2 copies of Teichmuller space, but only 1 copy of the mapping class group, why do we still get the moduli space?
Right. Okay.
I mean, I guess intuitively, maybe it's just like you're a phase space associated, you know, with a cotangent bundle over moduli space. But I guess I don't quite see exactly how that works.
Yeah, so that's one reason. Like you said, there is a different description of the phase space that is cotangent space of moduli space that would give you immediately that answer. But you can also see it from the Teichmuller times Teichmuller mapping class group. So if you have a section on something like this, then so it means that, let's just suppose this is a torus, but it's the same thing for any surface. So it would mean that it's a modular form with respect to the diagonal actions. So something like this. 2k, let's say, and f of tau. This would be what this means on M11. And this is literally, so there is just a diagonal mapping class group action. But this is like any function. It doesn't depend on homomorphically, so it's any function in modular space. And the fact on Teichmuller space, the fact that it has this diagonal invariance in the mapping class group action just means that it essentially only depends on the modules. This is usually what we do in 2D CF.
Thanks.
Yeah, I think I'm also done. So
Does this give the same answer as Kotler and Jensen?
it does, yeah. Except that I don't completely understand their modular sum. So if you do the same thing after, so they do some kind of sum over relative Dehn twist as well. I don't understand what they're doing there, but so this is not included in this answer. But apart from that, it gives the same result.
There's the measure as well.
The measure I was not super careful to fix because that doesn't. So you're talking about the fruit doesn't measure. Yeah, so that I haven't really computed that. I also just took from there.
But that measure is the thing that gives you the ramp, right?
Yeah, I know.
Okay, so
I don't have an independent computation of that. But yeah, as we discussed, there's also an issue that you should somewhere the mapping over this relative Dehn twist that is a bit subtle to do in this context. But yeah, so the same ingredients that they computed match with the same ingredients, and then they compute some additional things that I haven't checked. Right. Yeah, thank you very much.